So this video deals with polyprotic acids. Polyprotic acids are things like H3PO4 or H2SO4. H2SO4 is a really significantly different acid than all the other ones, which at some point I'm going to have to address, at least in class. I don't know if I'm going to make a video on that. Most polyprotic acids, however, are weak, and the Kas for successive ionizations or removal of hydrogens are smaller and smaller values. So just like when we did a strong acid or the weak acid, the one that's going to be critical in terms of determining the pH in a polyprotic acid is going to be the first ionization. Because the second one, the difference between the first and second one is 10 to the minus 5. So the second one is going to cause like 1/10,000th or 100,000th more hydroniums to enter the water. That's not going to affect the pH. It's too small a change. So most of the math will involve the first ionization, and then if we want to know the concentration of the other species, like if we want to know the concentration of the HPO4 or the PO4 3-, we're going to have to make a little bit of substitution, do some skilled substitutions basically. Okay, let's figure out what the pH is. Let's look at the first, the Ka1, which is going to produce the vast majority of hydroniums here. Right? So I've written out this equation which just shows the ionization of phosphoric acid and the removal of one of the hydroniums, which is why we're using Ka1, which is for the removal of the first hydrogen. Okay? And what I've got here is a usual ice table. I got 5, 0, 0, and I've got the usual minus x plus x plus x. And I'm going to make the usual assumption. I'm going to go, this is 5 minus x, right? That's a negative, right? This is x, this is x. And I'm going to say, oh, but this isn't changing by much. Why? Because it's 10 to the minus 3 here. So this is probably less than 5% of 5 is what it's going to change by. So I'm going to do x, and I'm just going to 5.0 over here. And then I'm going to solve for x. Now, as usual, when I solve this, I'm going to an x value that is relatively small, and the number I get is 0.19 molar. And I can always check this on the side if I'm 0.19 over 5, and I can take out my calculator and see what I get. So I'm going to do 0.19 divided by 5, multiply that by 100, but I probably know already that I get 3.8 times 100. This is 3.8%. So this is a pretty good assumption. It's less than 5%. And now I can just take the value I got, the 0.19, and I can take the negative log of that. So log of 0.19, close parentheses, and I get 0.72 is my pH. And again, I can always get my pOH and all the other stuff once I've got the pH. But once I've got these guys, I can use that like box diagram to get the other concentrations. All right, now that tells me basically this. I now know the concentration of the following things. I know the concentration of the H+, it's 0.19. I also know the concentration of the H2PO4. Now it's going to further ionize, but the amount it's going to change by is going to be insignificant, okay? We'll do an ice table on the following page, but I'm going to hold on to this number. Make sure we're clear. This concentration here, that's also the concentration of the H2PO4. That's also equal to 0.19 molar. All right? Okay, so let's look at what happens now with the next step in the process, right? So let's say you want to know the concentration of the hydrogen phosphate, okay? Like we want to know this one here, and then we want to know this one. Well, each ionization happens successively, but we have to use the values that we've been giving. And these numbers right now are going to be pretty darn important because we know 2 of the 3 items, okay, in the next equilibrium expression. Watch. So this is our next, this is Ka2. I have the value over here, and again, the equilibrium expression is going to be 6.2 times 10 to the minus 8 is equal to the HPO4 with the 2 minus on it, okay, times the H3O plus. So suppose we're going to make more H3O pluses, right? But we're really not, and that's the idea. And then on the bottom here, we're going to have H2PO4, and that's just minus. All right, I'm not going to do the whole ice table here. I'm just going to do it to the side. We're going to assume, now this guy right here, we already know this. This guy's 0.19. Now supposedly he's going to go down by x, but x is going to be, so our table in our brain is like 0.19 minus x, okay? This guy over here, he's starting at 0, right? He's going to go up by x, right? Right, so he's going to go up by x. And this guy over here is starting at 0.19 as well, and is going to go up by x. However, now look how easy the math is here. Because what ends up happening is when we substitute in, we get the following. We get 6.2 times 10 to the minus 8 is equal to, okay, x times 0.19 over 0.19. Now, of course, I'm going to just erase and make this. This is supposedly plus x, and this is supposedly minus x, right? But this is approximately equal to just basically x times 0.19 over 0.19. So these guys just kind of cancel each other out. And so the actual concentration of the HPO42 minus is literally 6.2 times 10 to the minus 8. That will be the concentration of the HPO42 minus ion. And you can see how that concentration is significantly less than 0.19. So clearly, okay, the value of X is not going to impact in any way the 0.19 molar hydronium or what is it called? Dihydrogen phosphate? Is that right? I think it is. All right, now, you can then do the third one if you want. And again, you're going to make some of the same exact assumptions. Now, this is a really small value. This is times 10 to the minus 19, okay? I don't think I drew that very well. Which means, again, we're going to assume that the changes that occur here, there's going to be almost no change in hydrogen. So we can start off with this is still 0.19. And you can see it's going to go up by x, but that's going to be really tiny. We also now know the concentration of the HPO4. We got that right here, okay? That's 6.2 times 10 to the minus 8. And again, the same thing. This starts at 0. This goes up by x as well. This goes down at x because this is 0. We know it's going to shift to the right. We know it's going to go up by x since all the coefficients here are nice, happy little ones, okay? So that makes our math problem easier. So we set up the same exact problem here. In this case, we end up with 0.19, that's our H plus, times x over the 6.2 times 10 to the minus 8 is equal to 1.6 times 10 to the minus 19. Now, this is the H plus that we got from the first ionization of the acid. This is the change that's happening to the one ion that we have not produced yet. And this is what was produced in the second ionization, okay? And so when we solve this problem, we get a value of 4.8 times 10 to the minus 13. Did I get that right? No, I didn't. 1.6 times 10 to the... Pause this. Okay, I made a mistake here, so I'm going to... This is a tiny mistake. This is 4... Sorry, I wrote the answer down over here. So